Everyone. So today it's my pleasure to welcome Professor Marian Mrozek from Poland, who will be giving a lecture series on combinatorial topological dynamics. And today will be the first lecture. Yeah, thank you, Marian.
Thanks, Marian, for the invitation. It's a pleasure to speak here on this forum. I have to say that my knowledge on machine learning is close to nothing. I mentioned to Marian that we have a small group of researchers here in Krakow working on machine learning, and sometimes I listen to their talks. So that's all what I just capture from their talks. They already use some methods in topological data analysis in their research on machine learning. So my belief is that because they use it only for static data, so my belief is that when you combine this with this machinery developed over the more than 100 last years in dynamics, it might be also useful in machine learning, but the listeners are here to decide. Okay, so maybe here is a very brief, in a few minutes, recall of the story of topology in classical dynamics. So I think it all started with Henri Poincaré. In 1892, he published a paper, Analysis Situs, which is considered by most mathematicians as the starting point of modern topology, but also on dynamics. Because Poincaré at that time worked on the n-body problem, interested in the stability of the solar system. And he realized that the quite advanced at that time already machinery of differential equations, they were able to formulate the problem, to write the equations, but they were also aware that the analytic tools are not sufficient to find the solutions. And without the solutions, it was difficult to address questions like the stability. So Poincaré decided some other approach is needed. And on one hand, he decided to do a kind of qualitative analysis of differential equations. So instead of trying to find solutions or approximate solutions, just try to predict its features just from looking at the right-hand side of the equations. And then he realized that some new methods, which later turned out to be called topology, might be useful. And the story is quite interesting because he actually came up with the main ideas of present-day algebraic topology, namely homotopy and homology. And the mathematicians who looked at this found these topics so interesting that the algebraic topology started to develop very rapidly in the early and mid-20th century. So that soon the topologists forgot about the origins, what was that stuff invented for, and they just were absorbed in the problems in topology they found in solving many problems. So actually it took some time before applications which went beyond the work of Poincaré appeared. And probably, I just mentioned here 4 milestones. So everybody probably knows the work of, or at least heard about the work of Marston Morse, who in 1934 published a paper on the relation between the topology of a compact manifold and the gradient vector field on such a manifold, and not only the vector field, but the dynamics such a gradient vector field generates on the manifold. So it was exactly what Poincaré wanted, the direct connections between topology and dynamics. But then again, several years passed, and probably another milestone was by Polish mathematician Tadeusz Warzewski, who in 1947 published his retract theorem, just a criterion for a topological criterion for the existence of bounded solutions in differential equations in dynamical systems. But it was among the tools which could be directly applied to differential equations. And I'll speak about it a little bit more in a moment. And then the last milestone I want to mention was Charles Conley, who published a booklet in 1978 about what is nowadays called Conley index theory. This was an algebraic invariant with roots in Warzewski retract theorem, which turned out to be much stronger than Warzewski theorem and provided machinery for proving existence of various types of dynamical features in dynamics. So this is the brief recall of these milestones. Maybe one more comment. After this Conley's paper, actually this was not only this booklet, several papers with his students, because most of his PhD students also work on this theory. And then until late 80s, several new results appeared in differential equations based on this theory. But then people realized that to go further, it's difficult because of limitations in analytic tools, not in terms of finding solutions, but in terms of finding these invariants, actually. So it was a progress. You could get much more with the Conley theory, but still not as much as one could hope for, again, because of analytic limitations. And once the computational topology started to develop at the very beginning of the present century, suddenly turned out that this machinery also provided what was missing at that time, namely these invariants could be computed by algorithms, even rigorous algorithms. So that revived the interest in the Conley theory. Okay, so this was the brief recapture of the story of topology in classical dynamics. And now I want to go into some details, but mainly about this Conley theory. Of course, this is a biased choice because there are many other topological tools in dynamics. For instance, topological entropy or a topological degree or fixed point index and several others. But of course, I talk about things I'm most familiar with. And before I start to go into details in the Warzewski theorem and Conley theory, I just want briefly recall the slides I showed in the Toronto conference last fall. This symposium on machine learning and dynamical systems. Namely, the way it worked originally, it was that you are interested in the dynamics of an ordinary differential equations in the sense that you ask questions about existence and stability of stationary solutions, periodic solutions, homoclinic or heteroclinic connections, or even chaotic invariant sets. And just the Conley theory in particular and several other topological invariants provided that machinery. But as I mentioned, even this is already progress in the situation when you have no exact solutions, no exact formulas for the solutions. You still can get progress via these invariants, but even these invariants require some analytic computations, which was a limitation So in fact, at the turn of the 20th and 21st century, people started to use computers to find these invariants, and that required the discretization of these differential equations. So numerical methods, which on one hand, it's a good idea because you can get these invariants. On the other hand, it raises questions about the correctness of such an approach, because a discretization is only an approximation. So actually, in many situations, you can get around this problem because you can do so-called rigorous numerics. That's not the story of the talk today, so I will not touch this any further. By the way, please feel free to interrupt me if you have some questions or comments. I understand from Boumediene that the time is not so very strict, so that should not be.
Do you mean ODEs of dynamics, not dynamics of ODEs?
Dynamics was a kind of approach to ordinary differential equations. This is the way I was taught and the way I understand this. You feel that's differently, that the differential equation started from dynamics? Okay, the way the mathematicians understand the dynamical system theory, because of course, if you go back to Newton and physics, in that sense, you're of course right.
Okay, thank you.
So thanks for this comment, because I as a mathematician, of course, when I speak about the dynamical systems, I understand mathematical theory of dynamical systems, or so-called qualitative theory of differential equations. But of course, in that sense, yes, everything started with Newton and dynamics in physics. Thank you.
What was the word? Coadditive?
Qualitative.
Qualitative. Thank you.
Qualitative, yes. Instead of quantitative, where you just want these formulas.
Of course. Yeah. I just missed the pronunciation. Thanks.
Qualitative, yes.
Thank you.
Okay, so now the situation is as follows. Now that it's important to see this split, because differential equations, dynamical systems belong to the world of continuous mathematics. But once you discretize, maybe you do not think this way, but once you do algorithmic computations on computer, you are already in the world of finite mathematics. Any digital computer can store only maybe huge, but still finite amount of numbers. So you enter the world of discrete mathematics. And now what I understand might be of interest in this community is the situation where you know your dynamical system only from a data set sampled somehow, either through experiment or from observations, maybe just a time series or collection, a cloud of vectors, a sampled dynamical systems. And mathematicians tend to solve problems by bringing the problem to the solved one. So it's quite natural to go this way. So what people do is that just take this data set and try to write down a differential equations, purely artificial, so that maybe just take a polynomial of high degree, and just try to fit these coefficients to the available data. And once they have a kind of good representation, they go along this path, which is already quite advanced and developed. But now you see that the situation is a little bit strange, because you start from finite sample, which belongs to the world of discrete mathematics. And you just go to this world of continuous mathematics because of availability of tools. But it would be more natural just to try to take this direct path. And this is what this combinatorial topological dynamics is about. So to come up with a kind of analog of vector field, differential equation, dynamical system, but in a combinatorial setting, and adapt these topological invariants available in the classical mathematics to this new setting, so that you can go directly instead of coming up with this differential equation. This is particularly important, I think, in situations where your data cannot be modeled by a differential equation which is not from some first principles like in physics. But instead, for instance, this is data taken from biology, in particular molecular biology or population biology, where it's very difficult to write precise equations and even more difficult to measure the possible coefficients. Physicists are very advanced in terms of experiments, and they can measure precisely various coefficients, and they know that these coefficients have really physical meaning, whereas in other fields, it's often very vague. What is the exact meaning and how to measure the coefficients? So such straightforward work would be even more justified in such a situation. Okay, so this is what I want to do, but today I just want to explain this classical path, and in the other two lectures we'll go along this proposed new way. So roughly I split my lecture into classical Conley theory today, Conley theory in combinatorial topological dynamics, I think in 3 weeks, and then one more lecture in January where I go even deeper into concepts related to Conley theory, Morse decomposition, connection matrices, more advanced invariants based on Conley theory. So classical Conley theory. Let me start with fixing some notation. So let X be a topological, maybe compact metric space. In practice, you can think about X as a subset of the Euclidean space, but for the theory, it's enough to consider even a locally compact metric space. Then I'll consider T to represent time, which means I take T to be R if I consider time to be continuous, or Z discrete. And then my definition of dynamical system is just a continuous map from X cross T into X, continuous such that there are two axioms satisfied. Phi of X0 is X, and phi of X TS is the same as phi of X T plus S. So this is a concept modeled, of course, by solutions of autonomous differential equations in Rn. And as usual, in terms of continuous time, we call it a flow. In case of discrete time, we call it a discrete dynamical system. Then I'll denote by phi X the so-called solution through X. So this is just the map which goes from T and assigns to T the phi of X T. So this is solution through X. And another map which is sometimes useful is the translation map. Looks similar, but now the argument is from the space, and you also assign. So you fix either first or second argument, and then you speak about T-translation map. This T-translation map is particularly interesting in the case of discrete time, because then you often denote by F this translation by 1, and you call it generator. Because once you know the generator, you can reconstruct from the generating by iterating. You can reconstruct the other iterates. Of course, for that you need this to be one-to-one, but actually this follows when we consider T just to be R or Z. Then because of this axiom, there is always the inverse. But sometimes you also consider only positive time, so R plus, Z plus, then I write T plus here, and then I'll speak about semi-dynamical system. Okay, so this is about dynamical systems. Now invariant sets. So let me start with first terminology for some very special invariant sets. So the trajectory or orbit of X is the set which I'll denote phi of X, just all the points along the solution. And I called X stationary if the trajectory is just this point, singleton, so it's just no movement. I call X periodic if there exists T in T plus such that phi of X T equals X. So in particular, every stationary point is trivially periodic, but not vice versa. If there is a minimal positive such T, then it's called minimal period. And then the concept of invariant set, because both stationary and periodic orbit are examples of invariant sets, but the general definition goes through the concept of invariant part. So the invariant part, so now I take N, a subset of X of my phase space, and the invariant part of N is defined as the set of points in N such that the whole trajectory of X is in N. And I say that N is invariant, or A, if its invariant part by the way, maybe I should write it this way. Sometimes it's important to also mark the dynamical system in the notation, but if it's clear from the context, I often skip the other argument. So if the invariant part of the set A is equal to A, then I call the set invariant. So it's easy to check that every stationary, every periodic point is invariant. There are some other invariant sets, so-called alpha and omega limit sets. So alpha of X is defined as the sets of Y in X such that there is a sequence of times limiting in minus infinity such that Y is the limit of phi X Tn, and the dual concept of omega limit, you just reverse time here, you go here to plus infinity. So these are called alpha and omega limit sets, and you also prove that limit sets are invariant. So the Conley theory tries to assign topological invariants to certain invariant sets, not arbitrary. We need a special class. We'll come to that in a moment. But so here are some examples. So this is now a picture, just stationary points. Here an attractor, here another attractor, and a periodic orbit here. Here time is, of course, continuous. And for instance, you can ask about the limit set for the point here. Maybe I just mark it. And you can check that the omega limit set is actually this stationary point, so invariant set, and alpha limit set for this point, when you go backwards, you just keep approximating this periodic trajectory. So the invariant alpha limit set for this point is this invariant set, this periodic trajectory. So these are some simple examples. So again, I'm maybe biased, but my understanding is that the main goal of the study studying dynamical system is so-called asymptotic dynamics. So the asymptotic behavior of solutions. So the behavior of solutions as time goes to infinity or to negative infinity. And the interesting part is that up till mid-20th century, the mainstream of mathematicians assumed as a kind of obvious that the limit set may be just as in this picture, a stationary point or a periodic orbit. Of course, there are mathematicians who were aware of the situation that it actually may be more complicated. But since only analytic tools were available at that time, it was very difficult to even visualize what this something else could be. So it turned out, with the help of computers, that people, the mainstream of mathematicians, accepted the fact that actually you may have quite complicated invariant sets, so-called chaotic limit sets, which wouldn't be probably discovered by mainstream if not the presence of just computer animations, and you can then easily see what's going on. Okay, we'll go back to that later in this talk, but now to the Warzewski theorem, because it's actually the root of the Conley theory. So Warzewski was interested in the following situation. It was presented in a simplified form, but it's enough for this lecture. So it was slightly deeper in his original paper. He took a compact set. In my picture, this is just the square, but any compact set in the phase space. And then he assumed that he can somehow understand the behavior of the solutions along the boundary of this set. So let's say that trajectories go up here, go down here. Here they go in, here also in. There is a kind of tangency. So this is a picture which is on purpose very simple. And then he looked at what he called exit set. So the intuition is that the exit set is maybe this part of the boundary where the trajectories go out, and here is another part of the boundary where the trajectories go out. And his observation was that, I think, first, in a simple example like this, that since this exit set consists of two pieces here, so whatever is starts here inside, if it leaves this set, then it has to leave either through top or through bottom. And because of continuity, the guess is that actually there must be a point, at least one point, where you cannot go neither up nor down, so you have to stay inside, because otherwise you will break a continuity. So actually, this was the way he formulated the theorem. So to formulate the theorem, let me give the precise definition of this exit set. So it's defined this way. This is these points in N such that there exists an epsilon greater than 0. Maybe I can move it a little bit down. Such that phi of x t is not in N for t between 0 and epsilon. So this is precisely what happens here. The trajectory actually might come back later on, but at least for some short time it has to go out. And the theorem says the following. So Warzewski theorem. It was 1947 when it was formulated. If N minus is closed and not a deformation retract, I'll explain in a moment. A retract of N, then of course N is compact here. N is compact. In the original presentation, it was more general, and then there this assumption was not needed, but also the conclusion was slightly weaker. But for us, this compact setting is better. Then there exists an X in N such that its whole trajectory is contained in N. So the definition of deformation retract, I need two things to explain it. So maybe in two steps. A subset X is a deformation. Maybe A subset N, because it's still, you can speak about a subset of is a deformation retract of N. If there exists a map or continuous map from X to A, homotopic to identity, from N to A, sorry, to identity on N, and such that are restricted to A equals identity on A. For this definition to be clear, it's also necessary to understand what does it mean that two maps are homotopic. So just in case somebody does not remember, I briefly recall two maps F, G from X to Y, X and Y are topological spaces. Two continuous maps are homotopic. If there exists continuous map H from X times 0, 1 to Y, such that if you take h of x 0, you get the first map, and if you get h of x 1, you get the other map. So the idea is when you can introduce this ht of x, this notation ht of x for h xt. The idea is that somehow you can continuously deform this map F via a family, parameterized family ht to the map G. So going back to this situation, you can guess that if we want a map which maps the whole square into this exit set such that it's fixed on the exit set because of this condition, and still this map should be homotopic to identity. So you start with identity, and then you won't just push things probably close to this side here because the end map must have values in A. At the same time, want to push them here, then something must be broken. So there is no such retraction in this case. And this is more or less the same explanation as I gave already earlier with this picture, that actually we have to come to a conclusion that something must stay here inside. The one possible way of completing this figure is by extending this to make here a stationary point and make it a saddle. But of course, this is not the unique way. The invariant set inside may be here much more complicated. This is the only way. So we know there is something inside. We do not know from this theorem what is the structure. The invariant set, we could say the invariant set inside, invariant part of the set N is non-empty. That's the other formulation. We could write it here. Okay, of course, the applicability goes beyond this simple picture because here, in fact, the fact that there is no deformation retraction may be obtained even simpler by the observation that the exit set has two components, connected components. And the set N itself is one connected component. So it's easy to see that in such a situation, there is no chance of deformation retraction. But for instance, when you take an example where everything, for instance, goes out from a disk, then the exit set is just the whole boundary. And again, the boundary of a circle is not a deformation retract of the disk, but to prove it, it requires more machinery. This is not something which you can prove by elementary tools. But the same conclusion, there must be something inside. So again, the simplest way to complete this picture is just to put here a stationary point. But things may be, of course, much more complicated here inside. Okay. Maybe this is good moment to also introduce homology. Both concepts, homotopy and homology, go back to Poincaré. Why homology? Because it's relatively easy to define homotopy. Also homotopy type, maybe I should add this here because we'll need it soon. Homotopy type. Namely, now you can speak about two topological spaces to be homotopic. If there exists maps from, of course, always continuous from X to G and from X to Y, sorry, from X to Y and G from Y to X, such that when you compose, you get not equal, but actually homotopic. So again, this is the notation for maps and for spaces. This is homotopic to identity on X, and when you compose the other way around, it's homotopic to identity on Y. So this is easily seen to be an equivalence relation. So equivalence classes of these relations are called homotopy types. And although the definition is quite simple and I think quite intuitive, even from the definition, although it's a lengthy task, but in many cases you can explicitly write down all the homotopies to prove that two spaces are homotopic. So an example, for instance, is when you take a disk, an annulus. So maybe let me mark it this way. An annulus and a circle. They are not homeomorphic, but they are actually homotopic. And the way you build the homotopy is you just take this radii and you squeeze along the radii towards the boundary. So the fact that they are homotopic is because of this hole. If you fill this hole, I already mentioned that there is no way to construct a homotopy. So it's easy to prove, relatively easy, at least it's constructive task to prove that two things are homotopic, but to prove that they are not homotopic, so they have different homotopy types, you require to prove the non-existence. And generally, it's not easy to prove non-existence. So actually, even Poincaré soon realized that he needs some tools which would let you just claim that two things are not homotopic, and this is why he came up with the concept of homology. So unlike homotopy, homology is something which is very good for computations. This is just pure linear algebra, but unfortunately the definition is complicated. So if I just give a very brief idea what homology is, because we rest a lot of homology in this lecture, but actually it takes time to learn it. And for simplicity, I give the definition not for an arbitrary topological space, but just for the geometrical realization for a polyhedron. Polyhedron, sorry. So like here in this figure. So it's constructed as a union of these elementary pieces, which are simplices, so vertices, edges, triangles, tetrahedrons, and so on in higher dimensions. And then to define homology, you need so-called chains. So in the simplest setting of so-called, so I'll explain it for so-called Z2 coefficients. This is the simplest setting. But actually, it's quite interesting to take also other coefficients, and the integers are actually most general. So this is the family of few dim simplices in this polyhedron. And then I can make it a sorry, so I need this way, let's call it SQ, and CQ of K is family of subsets of this SQ of K. And this family of subsets may be easily made into a group, taking, so this is an abelian group with symmetric difference as addition. It's also a vector space under the field of Z2 because there is trivial multiplication. Multiplied by 0 gives you the empty set. Multiplied by 1 gives you just the subset you took. And then you define the so-called boundary homomorphism. So you define this on the basis because actually individual, it's easy to see that this group or vector space, as a group, it's just free. As a vector space, it has a basis, and the basis is just consists of subsets which are singletons. So when you think about just a simplex as collection of vertices, so its boundary, it's defined to be the sum over I from 0 to Q of the faces, Q minus 1 dimensional faces. So you just skip the ith element, I minus 1, A, I plus 1, up to A Q. And then the homology, the Qth homology of K is just defined as the kernel of this homomorphism over the image. So the image of delta Q. For that, you need to prove that this actually is a subset of this, which is not difficult. But what is the intuition? The intuition is that although we look at all these chains, so these are these chains, group of Q chains. In this example, maybe I enlarge it for a moment. I just took a chain which is which consists of these edges along this red path, which for a moment will be green. Now it's again red. So when you take its boundary, so for an edge, the boundary consists of 2 vertices. So when you take just an edge and you apply delta 1, because this is a 1 simplex, so you get just 2 endpoints. But what happens here is, since this family of edges makes this loop, every vertex along this loop belongs exactly to 2 edges. And since our group operation is a symmetric difference, you get cancellations. So for this, so the boundary of this red chain here inside is 0. So this is an example of a cycle. There may be another cycle which goes, for instance, somehow like somewhere here, which goes around the same hole in the space. And these 2 cycles are equivalent. You see there is this equivalent since in this quotient group, because they are actually the common, the union of the red and green may be obtained as the boundary of the 2 chain which sits. What color will we use here? Maybe blue and maybe something thicker. So when you take these triangles in between and you repeat the computation of the boundary, so then all the edges which are internal will be cancelled, but all the edges and the boundary will be left. So this shows that actually these 2 chains are equivalent because they are boundary of the same chain, which means that both this green and this red chain capture the same element in the homology group and capture the same in practice, one would say capture the same hole here inside, because the homology actually is about capturing holes in the spaces. And for what is important for us is the following theorem, and we'll go to dynamics in a moment. Sorry, now it's too thick. No. Okay, now it should work. If X is homotopic to Y, then the homology groups in every dimension are isomorphic. Which means that if you're able to compute the homology group of two spaces and you find them not to be isomorphic, and for that, these are actually because of these Z2 coefficients, which causes that these groups are actually vector spaces, all you need is just to compare dimensions of this one and this one. And if these dimensions, at least in one grade, because you have now this word dimensions counts here in two meanings. One is the dimension of this vector space, but this Q is also called the dimension of homology. Sometimes it's also called the grade of homology. So if the homology vector spaces have different dimension in at least one grade, then you know that the spaces cannot be homotopic. By the way, this dimension is called Betti number. We'll also use that. So BQ of X is the dimension of the Qth vector space. Okay, so this is a very, very brief recall of homology. And now this isolated invariant sets where the Conley theory is sitting. So I put here already two pictures which explain the difference between isolated and non-isolated invariant set. So Conley thought about the Warzewski theorem, and he realized, and not only Conley realized, that of course there are examples where the Warzewski theorem is useful, but in practice, to guarantee, and go briefly to the Warzewski theorem, you see this condition here, you need this n minus to be closed. And this is not so easy to guarantee always in practice, to find such a Warzewski set. So here is an example. I still have this square and the maximal set invariant set inside. And in this case, this maximal invariant set touches the boundary. And this precisely is the reason that the exit set here is not closed. The exit set here consists of this point, because here the trajectory goes out. Maybe let me add this trajectory also here. And all these trajectories go out for shorter and shorter periods, because then they soon come back. But that's enough to be in the exit set. But here in the limit, this point is what we call internal tangency. And this internal tangency causes that the exit set is not closed, which means that Warzewski theorem could not be applied in this setting, which is a pity, because this is a quite severe restrictions on the applicability. So Conley thought that maybe I should look more deeply into what may cause this internal tangency. And the difference is between these two pictures. Here in both pictures, we see the situation of this internal tangency. But what is the difference? The trajectory which goes through this point in the boundary sits entirely inside N, belongs to invariant part. Whereas here we do have internal tangency, but later on, in forward time at least, the trajectory goes out. So this is tangency, but nevertheless, the whole trajectory does not stay in N. And Conley wanted to distinguish between the two situations, and he gave the definition as follows. N is an isolating neighborhood if the maximal invariant set in N is entirely contained in the interior of N. In other words, it does not intersect the boundary of N. In such a case, S is called an isolated invariant set. Then an S is called an isolated invariant set. So this case here, let's call it S0, is not isolated. And maybe not S0, but N is not an isolating neighborhood. Not isolating neighborhood. And here, this N is isolating. Here, the invariant part touches the boundary. Here, the invariant part sits here inside, does not touch the boundary. And the main contribution of Conley was that in this situation, when you do have isolating neighborhood, although it's not yet the situation of Warzewski's set, the exit set is still not closed. Nevertheless, he was able to prove, together with his students, that actually somewhere here inside, there is another compact contained in M. So now we can approach the Conley index. So first, another definition. N is isolating block. We had isolating neighborhood, now isolating block. Or sometimes it's also called the Warzewski set. If N is an isolating neighborhood and N minus is closed. So this is the special situation. And the theorem he proved with the students, it was 1978. It came in several flavors, versions in several papers, but the essence of the theorem is in two pieces. First of all, for every N isolating neighborhood, there exists M contained in N an isolating block. And the second part, if okay, let's add something to be more precise. S is an isolated invariant set. So let's start with this S inside. So this is our isolated invariant set. And I want an M such that, such that it's a neighborhood of S, even in interior of S. S is contained in the interior of N, but an isolating block. So if you are here, this is an isolating neighborhood. It's not so easy actually in this example to draw an isolating block inside, but you know there is one. So here you have to be very careful just to guarantee that all the time the exit set is the whole boundary, because this will be the case here. So this is one thing, but the other thing is if you have two such isolating blocks, but because there may be many, if M1, M2 are two such blocks, then they have something in common. Then when you take M, then when you take the quotient space, which means you collapse to a point the subset, which the part of the boundary which is just the exit set, then it's a homotopy equivalent to what you get from the other isolating block. And by definition, the homotopy type of this quotient space is what is called homotopy Conley index, but we are more interested in something more practical, which is the homological Conley index. Is just is denoted con. Star stays here for all the dimensions. Conley index of S is by the definition homology of this M1 over M1 exit set in all the dimensions. So you take this space.
I didn't catch that. Could you try again?
Sorry, my Apple Watch sometimes behaves like this. Okay, so you take this quotient space, you take the homology in all the dimensions. This is what is called the Conley index. It's well defined because they are homotopic. Whatever isolating block you take, there is at least one which is guaranteed by the first part, and any two give you the same homotopy type, so the same homology. So the Conley index is well defined. And here is an example how in practice you compute this. By the way, maybe one more addition. For those who are familiar with homology theory, this is under mild conditions, which I will not explain, the same as the relative homology of the pair. This matters from the computational point of view because the quotient space is not so easy to compute, but this is just, again, linear algebra, the relative homology. Okay, so here is an example of a trivial Conley index. So let's say our flow goes through our square. The exit set consists just of this right-hand side, right part of the boundary. I have to collapse this to a point. So just squeeze this, so this becomes 1 point. So we get then a triangle. We can still see these flow lines. And you can just use these flow lines to push everything to this point. And that's the homotopy type of this is the same as the homotopy type of the point. So this is so-called the trivial Conley index. And since everything here is relative, the exit set, so it's a point relative to a point, which means that actually this relative homology is 0. For our saddle, the computation, so the example I gave with the Warzewski theorem is like this. We know this is the exit set. We have to collapse this to a point. I do it in 2 steps. First, I independently collapse this piece to a point and this piece to a point. I still see my flow here. But then I still need to collapse these 2 points to 1 point. So for that, I need to just bend this a little bit so that they can come together somehow here and are collapsed to 1 point. So now you see I'm interested in the homotopy type of this piece. And now it's good actually to forget about the dynamics. It's not helpful here, but remember, this is almost like an annulus. You can just collapse things here to get the homotopy type, and you get the homotopy type of a circle with a distinguished point in terms of the homology. The homology will capture holes. So if this is our S, so the Conley index of S is our coefficients. So we only use Z2 coefficients. So let me stick to that. Z2, if Q, so in dimension Q, for Q equal to 1, and this is just because of this hole here. We have non-trivial cycle in the homology group and 0, 0 in other cases. Okay, more examples here. And there is a custom of writing the Conley index in the form of the Conley polynomial. So what is the Conley polynomial? Maybe here. Conley polynomial. You just take as coefficients this Betty number. So the dimension in fifth dimension of the Conley index of S multiplied by Q to the power N for N from 0 to infinity. But in practice, this is a polynomial, not a series. It's just for convenience because you do not know how far you should go. But since everything here is compact and embedded in, at least in Rn, a compact subset of Rn will give you always a polynomial here. So this means that just all the Betty numbers, so all homology groups are trivial, all Betty numbers are 0. This is 1, which means, look, here the exit set is empty. Everything goes in, the exit set is empty, and the Conley index is 1, which means that only 0th Betty number, which counts actually the connected components, is non-zero. This one we already saw. Here is the only dimension when we have non-trivial Betty number is dimension now 1, and beta 1 here is 1, because we have just one-dimensional vector space. So the polynomial is T. Here, when you collapse this boundary to a point, you should imagine you need 3 dimensions to do that. So imagine that there is a ball in R3 and that you just put this on top of the ball, and then you just try to bend things so that at the south pole, this exit set is glued just to a point. So that you get a 2-sphere. The homology of 2-sphere is non-trivial in dimension 2, which it's shown here that the Conley polynomial is non-trivial only in dimension 2 with the coefficient 1. For an attractive periodic orbit, this is the first situation when you have 2 dimensions where the Conley index is non-trivial. And you see already here that the Conley index will distinguish between an attracting periodic orbit and the repelling periodic orbit. The Conley polynomials are different. You may ask whether the coefficient here is always 1. No, it's not. You can give examples where actually there is a non-trivial coefficient here, but to have an interesting coefficient, you really need these Z coefficients, because for Z2 coefficients, of course, the only options are 0 or 1. Okay, what are the main properties of the Conley index and why it's so stronger than the Warzewski theorem? So the Warzewski theorem requires the Warzewski set to verify the assumptions, whereas Conley provided several features of this invariant, which allowed people to compute the invariant without constructing explicitly the Warzewski set. So the features, the main features are as follows. The first one, which is typically called the Warzewski property, which is just reformulation of the Warzewski theorem, is the Conley index of an isolating neighborhood or an isolated invariant set, because you can use this exchangeably, but maybe let's stick to an isolated invariant set. If this is non-trivial, non-zero, then S must be non-empty. This is just reformulation of Warzewski theorem. The Hopf property lets us tell something more about the features of the invariant set inside. Namely, if you compute the Euler characteristic, the Euler characteristic is the alternating sum of Betty numbers. So when you take the Euler characteristic of the Conley index, And if this Euler characteristic is non-zero, then there exists a point in N which is stationary, actually, such that there must be a stationary point. So in particular, in case of this saddle, the Euler characteristic here is 1 minus 2 is -1, which proves that actually there must be here a fixed point. The next property is additivity. If S may be written, if your isolated invariant set may be written as a disjoint union of two isolated invariant sets, so disjoint, then the Conley index of S in all dimensions is a direct sum of Conley indices of these two ingredients. Actually, this property was used a lot in the early applications of Conley theory for proofs of the existence of heteroclinic connections. The idea was that you constructed an isolating neighborhood so that inside the isolated neighborhood, you could locate two smaller isolating neighborhoods. And typically by just linearization, you are able to compute that they contain just a hyperbolic fixed point, so it's easy to compute the Conley index here inside. But then by some other properties, you also computed the Conley index of this big isolating neighborhood. And of course, the invariant set inside may be more than just what is here and here. And if there was a connection between them, that connection also would belong to the invariant part of this big isolating neighborhood. And that would violate this feature. So if you computed this, and so that there is no equality here, that meant that what sits the invariant part in this big set must be more than just S1 and S2. And with some other tools, it was then easy to show that this extra must be actually a heteroclinic connection. And the last property I want to mention is the homotopy invariance, which is actually the main tool, practical tool to compute the Conley index. And this makes the big difference to Warzewski theorem. If N is an isolating neighborhood for a family, for a parametrized family, of flows, then let's call it phi t. Let's say t from 0 to 1. Then the Conley index does not change. The Conley index of N with respect to flow phi t is const. So in practice, the way it was used to compute the Conley index, you took the system you were interested in and you tried to build a homotopy to a simpler system, a system where the Warzewski set could be constructed. In your original setting, maybe the trajectories were too complicated, but nevertheless, via the homotopy, you reduce the problem to a simpler case where you could construct the Warzewski index, and then you knew that the Conley index is as in the simpler system. Okay, so these are the main ideas about the Conley index. Very briefly now, on top of that, you defined more concepts. So the Morse decomposition of an isolated invariant set S is a finite collection of sets MP indexed by a poset capital P collection of isolated invariant sets contained in S, so isolated invariant subsets, such that for every X which is not in the union of this MP, for P in P, not in the union, there exists PQ in P indices, PQ in P, P greater than Q, such that the omega limit set of X is contained in the lower isolated invariant set, and the alpha limit set is contained in the bigger. So a Morse decomposition is actually modeled by Morse theory, and leads to a generalization of Morse theory. For those who are familiar with Morse theory, this is about compact differential manifold with a smooth real valued function on it and the associated gradient flow. And then you look for the, of course, I do not mention here all the assumptions, but you look at the critical points of the function, so where the differential is not an isomorphism, and you assume certain non-degeneracy. And then you actually prove several things, among them the so-called Morse inequalities, which give the relation between dynamics and topology. The Morse inequalities say that the number of critical points with Q-dimensional unstable manifolds. So you measure how many directions are there so that the flow is escaping from the stationary point. The number of Q-dimensional critical points is greater or equal than the Q-Betty number. In Morse decomposition, with Morse decomposition, you can prove an analog, an extension actually of such a result, which does not require a smooth manifold, just arbitrarily topological space and isolated invariant set. Instead of these critical points, you take just isolated invariant sets, like here. They are often called Morse sets here. And still you are able to prove Morse decomposition, Morse inequalities. We'll go back to that more when I speak about the combinatorial version of this, which is related also to this subject of connection matrices in my last talk. But okay, so I think here is an example of Morse decomposition. We already saw this one, but now my Morse decomposition consists, one Morse set is this periodic trajectory, which is an isolated invariant set, and there are three Morse sets which are just stationary point. So this is almost like in the setting of Morse theory, but at least one set is not just a stationary point, it's a periodic trajectory. This is my poset. These are the Conley indices of my isolated invariant set. We already looked at this. And you can formulate these Morse inequalities, but you can also get this from this connection matrix, which I will not explain now. It's called connection matrix because it reflects the existence of heteroclinic connections between Morse sets, but in an algebraic way, which is a little bit delicate. But in that sense, this connection matrix acts as the boundary operator in the homology of the so-called Morse complex. So for those who are familiar in Morse theory. Okay, so these were used, as I said, to prove several existence results. So formal proofs in dynamics, in particular also to prove the existence of chaotic invariant sets, although these results required a version of Conley theory, which, because what I explained is for flows, but there is also Conley theory for the dynamical systems with discrete time. And at least the first results about chaotic dynamics went via the Conley index for discrete dynamical systems. And I'll use this because I do not want to talk more than 90 minutes. That would be absolutely too much, but very briefly now. So these are the probably two most famous examples of chaotic invariant sets, the Lorentz attractor and the Smale's horseshoe. The Lorentz attractor concerns flows, the horseshoe concerns maps, but actually the proof, because the story of chaotic invariant sets is quite interesting. That's another long story, but very briefly. Lorentz tried to use computers in the early 60s of the 20th century to just make good weather predictions. So he solved numerically some PDEs, and then he realized that something strange is going on, and trying to attract mathematical community, because he was both meteorologist and mathematician, attract that something interesting is going on. He came up with actually an ODE in three dimensions, and this ODE behaved strangely. Namely, it behaved this way, that it looked like there is a point, even an attractor, which is invariant. It's a limit set for a point anywhere in the vicinity here. So if you start, so this is a picture in 3D. If you start here nearby, the trajectory is quickly attracted to this here, and it keeps rotating around one wing. After some time, it switches, keeps rotating another number of times about the other wing, and so on. And when you count the number of rotations here and here and put it as a sequence, it's a kind of perfect random sequence. So in that sense, you have this deterministic chaos. Lorentz was not able to prove that this really happens in this system. He only conjectured that something strange happens, and then he indeed attracted mathematical community. Some at early stage, there are doubts whether he is right. People said, oh, this is just because of rounding errors. You do computer simulation, so you make roundings, and these roundings are responsible, but people soon realized that it's not the situation. And the first attempts to explain what's going on went via a Poincaré section. So you just pick up here a plane such that the trajectories intersect this plane. And this reduces the study to the study of the map. And that something chaotic may happen in a map was explained by Smale in his famous example of the Smale horseshoe. So the way you can set up proof of the existence of chaotic invariant set is based, one of the ways, the first one, because actually I participated like 30 years ago in this first computer assisted proof that actually in Lorentz system there is this chaotic dynamics. And we went via Conley theory for the Poincaré map here. To build a Conley theory for maps is difficult in one respect. all these theorems, if we go briefly to that slide about the Conley index, I think this one. So the proof of this part, that if you take two isolating blocks, then they lead to something which is homotopic. This homotopy is based on following the trajectories of the flow. And in the discrete dynamical system, the trajectories are discrete. You cannot build homotopies along the discrete trajectory. So a completely new concept was needed, which takes the form of a special functor in category theory, one would say an algebraic thing, which surprisingly reduces to just homotopy in case your dynamical system is time t map of a flow. But nevertheless, it's a little bit complicated in that setting. So if somebody is interested, I can give you references to how such a Conley theory is constructed. But apart from this main difference that you need a replacement for homotopy, which takes a kind of algebraic form of normal functors, otherwise the theory is very similar. You have the same features. So the Warzewski property, when the Conley index is non-trivial, then the isolated invariant set is non-empty. The Hopf property, which is in that case called the Lefschetz property, because if instead of Euler characteristic, you have to take Lefschetz number. But if the Lefschetz number, so if this Lefschetz number of the Conley index, because the Conley index in the case of the discrete time takes the form of a map acting on a homology group. If that Lefschetz number is non-trivial, then there must be a stationary point. Also the additivity property and also the homotopy property. So all the same properties. So in terms of applications, this works the same way. The hard part is just that you need this special algebra to set up properly the Conley index. Okay, so I think this is more or less all what I wanted to say today. I had here the computation of this Conley index for the horseshoe, but I think it's already 90 minutes. So if somebody is interested, I can set references for that. It's not that important in terms of the other two talks, because I will not manage to speak about the combinatorial dynamics for an analog of maps. I'll speak only about an analog of flows. Nevertheless, the theory is present. We'll soon have a paper also about the Conley index theory in the setting of, in the combinatorial setting of maps on finite spaces. But that would require at least 2 more lectures. And it's still not published. So it's we have even not a preprint and not finished paper yet. Okay, so let me stop here, and thanks a lot for your attention. I'm ready to answer questions if you have questions. Thanks.
Yeah, thank you very much. Thank you. Any questions or comments? Yeah, it seems that there's nothing.
So I'll continue about the combinatorial.